Hi everyone, this is Ron Badum with Atlanta Functional Programming and welcome to another episode of the Haskell Study Group. Today we're going to be discussing folding lists or list folding, which is, for those of you who have been following us in the Haskell Programming book, our review of Chapter 10 that's in the Haskell Programming book. It's Haskell Programming from First Principles by Christopher Allen, Julie Moronuki. Today we're going to be discussing we introduced some of those concepts last week, just briefly showing you fold L versus fold R. We're going to be digging more deeply into those that information a little bit today, as well as talking about how to write your own fold functions so that they can act like fold L and fold R. And we'll be talking about a little bit about evaluations and how folding fits into evaluations and the associativity of both all the folding functions. Before we get started, a couple of announcements. For those of you who have been following us along on Sundays, the Atlanta Functional Programming Meetup is doing some schedule changes. We will start having the Haskell Study Group starting next week on Thursdays. So that means after this, we will see each other on Thursdays from 7:30 p.m. to 9:30 p.m. Eastern Time. Please look out to Meetup. For those of you who have been following us on Meetup for reminders, we will post the announcements on that today. Additionally, as all you know, Atlanta Functional Programming is looking for speakers. If you guys are interested in presenting a topic, we try to do a monthly meeting where we try to discuss functional programming topics in a language agnostic manner. So those of you who are looking for topics, whether it be in or interested in presenting a topic in any language, whether it be F#, C#, C++, or our standard, functional languages, Lisp, Haskell, OCaml, Elixir, what have you, please feel free to either directly message us here on Meetup with Atlanta Functional Programming, or you can contact us through Functional Programming Slack. I'm on the Lisp channel on Functional Programming Slack and has Bugram, and I'm also available on the Lisp Discord server under the same alias. So feel free to ping me with your topics, and we'll try and get you scheduled. So last time we talked about folds, I briefly mentioned this issue of what a foldable expression is, and I kind of introduced fold L and fold R through just showing their signatures and some brief examples. So fold R is this, and fold L is the following. And one thing to note is, and I'm just briefly showing them here, is I mentioned last time that both fold R and fold L are both types of foldable expressions, in that there's a type class called foldable, and it contains these evaluations, these reductions. Okay, so if we go and look up foldable, you can see that essentially there are many functions that can be implemented to be a foldable expression: fold L, fold R, fold map. We're going to basically focus ourselves in today's discussion on fold L and fold R, not even fold L1 and fold R1. There are some small additions in there. I still am not quite certain that I know the difference on that. I'm still working through some of those things, and hopefully later on, once we complete this chapter and some other chapters, we can get back to talking about those other versions of these foldable expressions. But To get started on the topic of foldables and folding, there's one thing that needs to be introduced, and that's this concept of what a foldable is. And generally speaking, folding falls under this topic called catamorphism. Now, catamorphisms are a mathematical term that essentially talks about deconstruction of data. Right? Cata means breaking down. Morphism means, if you recall, morphism means just kind of a functional mapping, right? The actual term of morphism actually comes from both cata and morphism come from the Latin version of what a morphism is. It's a structure. To be more precise, it's a structure preserving mapping. So what a catamorphism is doing is it's breaking down that structure and mapping it to something else. Okay. Why does that include folds, you may ask? Well, a catamorphism is the process of deconstructing a particular data structure and then doing some sort of transformation to it. It doesn't necessarily mean that, so they, it kind of breaks down the data structure to its base elements in an effort to transform them. And in addition to, it may return either the base element that upon which the function we're transforming on returns, or what it does is it may return a new version of the data structure. So it may construct a new version. It's probably a better way of saying it. Construct a new version of the data structure you're dealing with. Or it may actually create a new data structure. There are fold expressions that take in one data structure, deconstruct it, transform it, and construct a new structure. This is a very generic term for essentially anything that breaks down a particular data structure to its base elements and does something with it. Okay. Folding itself falls under this category because, as you can probably guess, a fold actually allows you to break down a particular collection and reduce it to either something of one sense, or it may end up, they're constructing a new structure. We actually saw a fold in a sense when we started talking about maps last time, because what a map does is a map, if you recall, basically takes in a structure and it takes in one type of list and returns another type of list. Okay, it's breaking it down in the sense that it is actually going to go into the structure itself and take each of the individual elements and does something with it. Now, in this particular case, in maps case, it actually goes into transforming it into another list. It will actually return a new list with the return types from the transformation function added to that list. But folds can also do other stuff. This is why maps tend to be actually a separate topic that we tend to discuss. But for the notion of actual folding expressions and notion of catamorphisms, technically, I'm pretty sure a map also falls into that category. And if you look in the book elsewhere, I've seen that they actually mention map too, as well as this structure breaking down transformation being part of the catamorphic behavior necessary to actually construct the list. So let's start talking about fold R for a minute here, okay? So we're gonna, fold R, as you saw here, is going to be taking a function of two arguments, all right? And it then takes in as well as another value of the same type as the second argument, and it returns a function that takes in a foldable expression of A and returns B. Okay, this is how you read this particular function signature. And one thing to note here is originally in GHC, this was a generalization of the original fold expression, which I'm going to just go ahead and write here in my buffer. Thanks to the reference from the Haskell programming book, I think it's important that we cover why this was originally written this way in Chapter 10. The original version from GHC 7.10 and older had a completely different foldable expression, and we could see immediately why this was the case. Okay, so originally we were taking a function of two arguments, particularly two different types. We took the initial value of the function of the second type. We took a value of type of the second argument of the two argument function. We then took in a list and we returned the actual value here. All right. You clearly can see now we're using the type construction of the data construction of a list of type A here. Between GHC 7.10 and newer, they've changed that and introduced the foldable expressions that we brought in. This merely so that this is a generalization of this. Okay, so now when you look at this function that when we put these side by side, GHC 7.10 and newer, you can see immediately that this function here is nothing more than a generalization of the second function B, right? And specifically, if we write this way, and I think this is a good way of putting it, we are essentially taking the data constructor of the list and creating a new list of type A, whereas here we're expecting the type to be some sort of foldable expression that implements the foldable type class. So that means there has to be an instance on the an instance of foldable on that particular type in order for it to be a foldable expression, and we could pass it into folds. This is kind of the same stuff that we talked about when we talked about type classes in general. I'm just reiterating it here just so that folks can be aware of what's going on. Now, one of the nice things about this particular thing is now you can also technically work through writing your own version of this if you want to use this kind of like thing and restrict it. There's this rule in Haskell programming that you could make your types more concrete, but you could never make them more generic. So you could certainly take this generic expression, which we have here, and restrict it on just a list by writing your own function. Let's say we call it myListFold R, and then we define it as our standard, function of two arguments. And B, we go in and we go ahead and create, initial value A. We then take in A and then return a B, just like what we saw here. And instead of this, we just go ahead and say myListFold R equals fold R. And this effectively will now, if we go and look at myListFold R, you'll see that we get the same signature that we would have had in the old version. This is kind of one of the nice things that you can do. If you want to put some aliases in some of the more generic expressions to make more stricter versions of them, you can certainly do so. Finally, I think like I said, with relation to map, I think it's important for us to actually see the differences when we look at map. So we saw my map earlier here with this, and let me go ahead and put this guy here in our buffer and put it side by side with what we saw earlier here with fold R. Actually, with the new fold R that we just wrote, actually with the old fold R. Let's take the old fold R. And you can see that here we put these side by side, and we change this to A and B. You can see that they're essentially an extension. Map is technically an extension of what, fold is just a kind of a type of map, because, map is a type of fold, because we're taking in a list here, and we are constructing a new list once we transform this function. In fact, you could probably even write this map here as a fold R just by doing it's because it's essentially a construction followed by an append. So you're creating a new list and then calling an append on it. So there is probably a way to implement map using fold R, but we're not going to be discussing that for the time being. One thing to note is kind of the evaluation rules when you're looking at this, because if we look at an example of map, take for example we do map +1 on 1, 2, 3, we know that from what we saw before, this is going to be deconstructed, because again we are taking this list. This list is nothing more than syntactic sugar on a con cell. So what this ultimately is just my map +1 on 1:2:3 empty list, and we can actually go through and convert this now to map to applying just a function on 1, applying just a function on 2, and so forth. And this is just us calling the function on each of these cases, based on how map is defined. In a similar fashion, you will see that fold R has the same kind of application. We'll talk about associativity in a minute, but one thing just to note here is just the deconstruction is basically applying is fundamentally the same between a map and a fold R, a fold right. The only difference is whereas map actually applies each function and returns of the final list, so it will construct a new list by doing a cons. You recall that in the map implementation, we can actually go in and essentially call cons on the f of x, and then we map the rest of the value until we get to the empty list. The fold will then replace each of the cons constructors that we see here. Okay, if you look at right here, we have a cons constructor here. We are in this case, we are doing in the fold case the application of the actual function that's being converted. So let me just show you this. So this could very quickly just be applied by doing the following. So this will then be set up. Just give me this 1 second here. So we'll go more into details here, but very briefly, this application of the function is just simply going to be 2, 3, 0. Okay, so this is the same thing that you could see here. Has the map. The only difference is where map is applied then cons. Okay, because we're constructing the data structure here. A fold is applying and then creating potentially a new type. So this here is essentially a different way of actually. It's another type of way of doing deconstructions and catamorphisms. Both map and fold use some sort of catamorphic behavior in order to do their jobs. To illustrate and show a little bit more about foldr and actually the underlying logic to implement the patterns that are associated with right folds and then eventually left folds, I think we'd want to revisit, and this is something that the code that's related to summing numbers. This is something that the book, I think, mentioned with a couple of examples, and I thought this was a good thing to kind of review. To begin with, you may recall that given some sort of, sum function and some sort of list, let's say first 5 integers, or let's do a simple 1, 5, 10 from chapter 10 of the Haskell book. You can see that this actually, gets evaluated into 16, but how does it get evaluated? Well, recall that the signature of the sum function is taking in a list of integers and then returning an integer, and we have two cases here. We have the case of the empty list where it'll return 0, or the case where we have, some sort of list where we're going to deconstruct it to x and the rest of the list, and we're going to apply essentially the addition function on x plus the sum of the rest of the list, which is our recursive call. So we'll go back, we'll keep on, applying this function here, right? This recursive pattern actually happens a lot in many different functions, if you recall. We looked at this with the case of length. We've looked at this case if we're running products. Okay, if we looked at product, which is the same kind of idea as sum, except we're applying a different kind of sense here. If we could certainly see that with product, we have a list of integers that will return an integer. We start with the case of the empty list and returns 1. And then if we return, the x with x's, we could see that this is going to be x times product of x's, and we see the same structure here, right, between the sum function signature and the product function signature. But this can also be applied to even cases such as concatenation or even length, right? The one thing to note is and to really see this, maybe concatenation will be kind of the final kind of example that we should really kind of cover. We take a list of lists and then concatenate them, and then we have, in the empty list, we have an empty list, of course. But if we do concat on, a list of lists here, we get where we have x's. What we'll do is we just do x plus plus and track the rest of the list. Okay. Now, in each of these cases, we have some sort of base case. Okay. In each of these cases, we have a base case. We have some sort of base case. Okay. Either where, some sort of in the case of addition, we have the additive 0. And this base case basically is any number or value that we apply the operation to will give us the same value as our initial value, right? So in the case of addition, we use 0 because the first value of the list is probably some sort of x, and x plus 0 equals x, okay? In the case of product, we have 1 because, any x value times 1 will always equal to x. So that, in the case of product, it's called it's multiplicative. Okay, so these things are called the identity value of the actual type that we're actually dealing with. Okay, so 0 is normally called the additive identity. The 1 is normally called the multiplicative identity. In the case of empty lists, it's just the identity of lists. Okay, the list identity is always going to be the empty list, because if you concatenate any value with the empty list, you're going to end up getting the first list that you started out with, because the empty list isn't actually adding anything to the actual list itself. So that's why it is considered the identity for the list category, the list type, right? This is important because when you're starting to talk about folds, knowing the identity of the type that you're dealing with is going to help deal with writing out the recursive pattern for a given foldable expression. In the case of fold right, it also helps you in the sense of, well, in terms of either fold right and fold left, it also tells you where either the stopping point or the starting point of the actual expression evaluation is going to occur. All right, we'll see there is a difference between fold right and fold left in terms of how it's going to be evaluated, and we're going to touch base on that in just a moment. But to begin with, I just want to take just a quick moment to make sure that people understand this particular idea. So I'm going to just wait a few minutes while, and if you guys have questions, feel free to post them. Okay, so looks like there are no questions, so let's continue. Okay, so let's continue here. All right, so let's go back to fold right, which is the first one that we're going to be dealing with. Fold right is pretty important to understand, and it can be implemented in several ways. All right. So to begin with, I'm just going to go back to what we had earlier, which is our good old function signature for fold right. We're going to go ahead and put this up here, and kind of show you how one might end up applying this. All right. So let's make my fold right just my fold R, take the same signature, okay? One way of actually implementing this, and of course we want to be able to say foldable T. Okay. One way of implementing this, of course, is could be actually, you know what? Let's make this. Let's go to a simple case. Let's do the original one, just because we're dealing with lists today, for the sake. And we'll go back and generalize this when we start dealing with more general types and foldable expressions later on. One way of implementing this, as we saw earlier, is that we can implement this using f, some function f, some value z, which is our initial value, and if we get an empty list, we can put in that z. Z is representing to be the identity of this. I normally use I. The book, for some reason, uses z. This makes it so that it's easier to know that I is for identity. You know, it makes kind of sense. Z's also could be considered 0, but you know, whatever whatever notation you use, whether it's Z or I, doesn't matter. It represents the identity value of the type that you're dealing with. It's very important. It's the identity value of the type that you're dealing with. So you need to look at the type that you are actually applying to, and you need to determine what is the identity value for that class. Okay, and for complex types, defining an identity would allow a couple of these foldable expressions to become possible. So if you're creating your own type and you're actually creating a complex type, try to think about what kind of identity value, what kind of base object is necessary in order for this to be, you know, used in a fashion such that, you know, the basic properties for identity is if you pass in any other value to it, or you apply any operation with the identity, you get the same value back. All right, this is the basic rule. And for most of the basic types and primitive types that are already available, we've already kind of discussed this. Later on, we're only going to be discussing kind of some simple examples, but as we're developing our own applications and our own types to build up kind of systems, this will become more and more important, especially when you're writing out reductions for certain type of information. So I can't stress that knowing your identity is going to be an important thing to learn about. Now, in the case of this myFoldR, once we have it and we have our, you know, our recursive case, we can just apply this as normal. You know, we just do f of x, and then we apply foldR on the values. All right. Now, one thing to note about this, and okay, so we apply this. Now let's just make sure that we're all good. We do a myInfo, myFoldR. We have our function. Now if we do myFoldR on plus 0, let's say 1, 2, 3, you'll see that we got 6. Another way of actually defining this is also using a case statement inside Haskell. You could also write myFoldR case or something like that. And you'll get the same, actually, let's just go ahead, and it's going to be the same fundamental signature. And we're going to just call this case, myCaseFoldR, just for the lack of name here. I could certainly use, actually, it's probably better to use myFoldR prime, okay? We are using Haskell after all. And in here, we can then, you know, define our definition where we take in some identities, some x's, and we look at the case of the x's. And if we got the empty case, we can return the intended identity. Otherwise, if we have this syntax here, and this is using the standard case syntax that everyone is familiar with, you can also use the same, you know, myFoldR prime on fi(x's). Okay, and again, this is going to give you the same function evaluation as we saw earlier with our simple example. Now, what is the difference between these two in terms of the evaluations? Well, first thing to note is the fact that when fold R gets a list, its evaluation follows right associativity. What does that mean? That means that our recursive call is going to be to the right of the expression. All right. So in this case, we would end up doing um, uh, the first call, if you will, of case. It would be best illustrated with the first case here with the myfold r prime. If we take, for example, myfold r prime with the additive function 0, 1, 2, 3, and this is just the same way fold r would work. What we would end up getting is we would end up first applying +1 and then calling fold r on the rest of the list. Okay, and 0, 2, 3, and then it will keep on going until, and the second addition. Let me just do the quick case here. We'll do this again. Evaluation +1 plus +2 for my fold r prime 0, 3, and it'll keep going here until finally we hit the final case where we have +1 +1 +2 +3, 0. Okay, so this is the evaluation. We keep going down until we hit the base case, and then we apply 0, and now we have the full expression. Everything is bounded. We can actually go ahead and do the evaluation. Okay. The one thing to note is well, there's a couple things to note. One is that the base case is the last thing to be actually executed in the case of a fold R, right? We are essentially doing, if you really want to think about it, a depth first evaluation of this. We're going all the way down to the leaves until we've exhausted creating the tree, and then we evaluate the entire expression, okay? And this is because since plus, the addition operator, is strict on both of its arguments, it will unconditionally evaluate the expression until it hits a case where it can actually run its operation, okay? Does this make sense for folks? Okay. Of course, this isn't. I mean, I'm sure you've seen through this, and you can actually evaluate this. One other way, which I thought was a pretty neat little trick from that the book mentions for folks to understand some of these, is using the concatenation operator to actually go and evaluate both my fold R and fold L. And we're going to use the concatenate operator to kind of like to show this. But the point of this evaluation and understanding of all this is the fact that since it is right associative, this allows us to use a right fold on a potentially on an infinite list, as well as on lists that contain a undefined or bottom value. And we saw undefined on bottom last time. It was essentially a representative of a never-ending evaluation. Okay. So by applying that, you could apply an undefined, like a prelude.undefined inside your list, and you can figure out ways of actually working through that list. Okay. So I'll give you one quick example here on this undefined part. Well, on the case of hold R with plus on a potentially infinite list, although in this case we're not really going to be infinite here. We're just going to just do the first 10 lists. If you could think of if you actually applied this on an infinite list, you'd have some problems. But you can also do this also on, $ take 10 of that, and you'll get the same result. What this is doing is takes from an infinite list a certain sample size, creates the finite version of the list, and passes it over into the right fold. Additionally, you have cases where you could also define like we have a function in Haskell called any, all right, which takes another foldable expression where you have a predicate. It takes in some sort of value of that foldable expression and returns bool, right? And if you pass this into, say, let's say even on an empty list, it'll say that we have true. But if we're constantly it will, and the reason why this works is what any does is behind the scenes, any essentially is an OR. It's a logical OR, right? So if we suppose we define this here, as such, let's take its signature. One way of implementing this, and this is probably how it is implemented underneath. Let's say we created the same version of this guy, and we actually go ahead and then say f of x's equals fold R, and then we pass in a lambda that takes in some two values, and we essentially apply the function to the first value, or b, and then b is potentially going to be the rest of the list. We just pass in this, we have the same expression that we would end up having. 1 second, there's a complaint here. No instance for oh, sorry. Let's do this on that. There we go. So now, if we apply this guy to what we had earlier, we would end up having the same sort of issue. And the reason this works is because, again, if we do any version on an empty list versus, say, if we go and call this repeatedly, which would, will certainly cause some issue. Like if I end up applying this on a repeat one, we'll have a never-ending loop because of the fact that it's not going to hit the first case. The first case where we apply the infinite list, it short circuits. If you look at the function definition here, right, it is actually short circuiting. It's applying this function to the first value, the head of the list. Okay, and if that's true, it's gone. Remember, we do short circuit evaluation when we're dealing with logical ORs in Haskell, just like we do with other programming languages. The first case that actually returns true will make the entire expression return true. Okay, so we'll only iterate as far as we need to actually discover the first true value before we exit. So that is a finite set of operations, which means that we could certainly use the right fold on an infinite list as long as that infinite list represents a structure such that the predicate can actually hit the first value that actually returns a true and exits the evaluation. In the case of the second case that we have here, like if I ran even on repeat 1, obviously repeat 1 is going to be never ending. It's going to create a never ending list, an infinite list of 1s. Since none of them are going to be odd, there's never going to be a case where we're going to actually exit evaluation. So if we run this in the REPL, it's just going to keep going until we actually stop the evaluation and abort it, or kill the process. It's more one of the reasons why I'm not actually going to go ahead and run this code, but I thought you should know. So the same thing actually applies to, let's say we run fold_r on addition, adding numbers. Again, remember, addition operator is unconditionally going to evaluate the list. And we have a list with us that has our good friend, the undefined function. Okay, remember u is undefined. Okay, it's going to be, sorry, not u, prelude undefined. Let's do this. Undefined, remember, undefined is an exception inside Haskell. If we have an x's with 1, 2, 3, 4 undefined, and we tried running fold_r on addition with these x's, we're going to get a exception thrown because, naturally speaking, we have in there a value that's going to be throwing that exception. Now, if we go and if we know that that's going to occur, right? If we know that that's going to happen, we can actually cut that guy out and then just simply apply the reduction operation, the fold operation, on just the subset by just simply grabbing the 4 that we need to go and evaluate on. All right, and this applies to any sort of thing. If we do the same thing with if x's was 1, 2, 3, 4 with say the concatenation operation, okay, you'll see that we'll have an issue if we do fold_r on +0, 1, 2 $, 1, 2, 3, 4 plus undefined. You'll see that we'll get a prelude undefined, but if we go and do what we did before, which is obviously cut that guy out by doing take 4 of our friend 1, 2, 3, 4 plus undefined, it's going to ignore the undefined altogether because, again, we actually cut it out in the subset that's actually going to be returned, and we're just going to go ahead and run this. There are cases where this kind of pattern of lopping off the value is going to be changing the results of the actual function. An example of this is if we drop the undefined value of this bind and we pass that to length, technically we are actually getting the wrong length of the actual list because we're only getting the subset of it. But it can it will create an expression that works. It will allow you to actually evaluate the expression accordingly. Take is much like all the other operators that we've seen last time. We've talked about take. It is a non-strict evaluation. Remember that. So it has a finite limit, and it only returns the evaluation of the infinite list that allows the stopping condition to be satisfied. Okay, so if you ask for 10 elements, it only evaluates 10 times, and so forth. Okay, but because it stops returning elements, it is going to change some of the behavior of this. Okay, it's interesting actually because you could have an example. Say this is something that the book had that I thought was pretty interesting. You had this function that this data set that has undefined in it, and you call length on it, but by calling it after calling take 2, take 4, and then x's. Okay, this expression here. Let's review this expression. What we have in take 4 x's. Okay, we pass x is now 1, 2 undefined. Take 4 x's. obviously it's going to stop until I hit the end of the list. And in this case, undefined is part of the end of the list because we're asking for 4 elements and there are only 3. So it's going to actually return all 3, 1, 2, and undefined. But because we have this take 2 in front of the take 4, we're actually still doing what we did before, which is actually lopping off the undefined values, which makes the data set valid for length to actually go and run its evaluation. Because 4 will never allow us to, the the take 2 will never allow us to actually hit bottom. Okay, so take 4 could hit bottom, but take 2 cuts bottom out of the take 4 result. So the rest of the expression will become valid. So I thought that was pretty neat. The right fold in the recursive case has this case where we are now passing in, we're taking a value and we're passing it into the expression, right? Where the first argument could technically be its own expression, but this expression has to be a strictly evaluated expression because it's passed in into the function that, and ultimately is going to be a value that's going to be required to be existent in order for the rest of the evaluation to occur. But if x is if the x's is an empty list, we need to provide some sort of initial cons value into this. This is where the identity becomes important. Okay. So what fold R does in order to actually accommodate this, it actually forces an initial cell to discriminate between the base case, which is our empty case, and our non-empty case. So the first cell of the actual list cannot be undefined. What do I mean by that? That means is there cannot be a case where you do fold R plus 0 this, because this is technically invalid for sorry, the second case should be some sort of invalid, just because once you have something like this, it's going to iterate through the first initial cons cell, all right? And if it ends up being empty and you can't apply the operation on it, it will end up throwing up some sort of exception. So Haskell behind the scenes takes care of some of this, these edge cases, and allows you to preserve some of the structure of the evaluation when you're actually evaluating. Okay. An example of this is an example that I think the book really did an interesting thing that we can cover is the following. Let me just pull this up. Yeah, so this is from page 357 in the book. So I'm just going to go ahead and mention this example that you guys can look at. Haskell book, chapter 10. And this example here, I think, is a very interesting example where we're ignoring 2 arguments and where we're just returning, some sort of number. We're applying 0 to it, and we're just getting 5. Okay. In this case here, this will work just as normal. It'll just keep returning 9001 because we're not actually doing anything. All right, but what's funny is this also can work on an infinite list. So what do I mean by that? Let's say that we do, sorry, not an infinite list, a list that contains a bottom value, undefined, okay? Because here, since we're ignoring all the values in the list, and we're just returning a constant value, it's just going to, it will never touch that strict evaluation case, okay? And this also applies to if we go and decide to do something like this, 1 to 2 plus undefined. This here will also work the same way. So for those of you who might be wondering why 2 underscores, it's because the fold expression has to take in an argument of 2. Remember, go back. I recommend you looking at the function definition to validate that why that's the case. And you can see that this is actually going to be ignoring that too as well. But if we pass in the bottom value as a expression, this naturally is going to end up evaluating the first expression because remember, it's not empty. We're not going into the base case here. We're going into this case, okay, when we're dealing with the bottom value. Okay, we're going into the recursive case. And since undefined is obviously going to be throwing an exception, we're going to throw the exception. So that's why this is occurring. As long as the bottom value, the undefined value, the prelude.undefined, is part of a set where it's like the last value or it's somewhere in the actual data structure, partial evaluation of a foldable expression can occur. All right, there are some ways of allowing it to occur depending upon the actual anonymous reduction function that you're using, like in this case where we're ignoring certain values, okay? But if the first value, the very first value of the list, if that is undefined, then we are in trouble, all right? So let me just show you this one more example, just kind of like this. This doesn't just mean if we pass in undefined. If we pass in undefined plus cat, you're going to end up having the same thing, all right? Because you can certainly do that, right? You can pass in anything here, and as long as, since it's the first value that's being passed in, that is what's going to ultimately determine whether or not it is going to be evaluated or not. I'm going to pause just for a minute here just to do that. My apologies for folks that are here. Can folks on the Hangouts hear me? Okay, good. All right, then we're golden. All right. One final thing noting about the advantages of the right associativity behavior of the right fold operator function that we've been discussing so far. And one is related to the structure that we're dealing with. Actually, before I start talking about the final piece of the right associativity, one thing to note is this discussion that we're talking about bottom and undefined, a lot of it has to deal with, again, with more of the strictness and non-strictness nature of evaluation inside Haskell. And we're going to see more examples of this as we continue our exploration of it. I think it's necessary to know that non-strict evaluation has its advantages in many, many different cases. And from a performance standpoint, it's going to, if you know what you're doing and if you know how to design your types and your collections, you can actually take full advantage of this non-strict evaluation to actually create fairly efficient programs for a number of use cases. And we're going to be discussing that as we keep going through our exploration. But to talk about this, we need to also talk about one of the final advantages of, like, the right associativity of the right fold operator, and that is fold R being right associative means our traversal of our spine. Okay, remember what the spine is. The spine is, when we're talking about lists especially, the spine is represented by the cons between the first and the rest of the structure, right? Traversing the rest of the spine after evaluating a particular value, that traversal is lazy. It doesn't occur unless it is asked for by the result of folding the rest of the list, okay? So it is not forced at all. The only time it is forced is based on, it is not forced unless the operator, the foldable expression, the expression that we're dealing with, requires it, at which point it is forced, okay? So an example of this is actually another folding expression, which is called const. And this const expression basically is nothing more than a 2-argument expression that returns the first argument always, okay? And how would you implement such an expression? Well, I think we've seen this before, right? If you are defining a myConst here yourself that has this expression that takes in this and returns the first value, what's the best thing you could do? Well, that means that you are ignoring this every time, right? So, sorry. So now what we could do is if we do const 1, 2, you see this, const 2, 1, you see this, myConst is the same thing, 1, and you get the same thing. What's going on here? Well, what's going on is because the const operator is ignoring the second argument being passed. It is just going to be it's completely and almost always ignored, and that means the rest of any sort of evaluation is just going to be pruned from the evaluation prior to the actual result being returned. And you can leverage this in quite a few cases. Like, for example, if you do fold R const, alright, 0, 5, you'll see that the first time that this gets called, it's always going to be 1. And why is that the case? Remember how this is evaluated, okay? Go back to this case right here. This is essentially going to be, if we're using the const case here, if we're doing const with this expression, what is this doing is, this is nothing more than doing const 1 of const 2 of const 3 of const 4 of const 5, 0, right? You may think that this is what's happening here, right? But this is not what it is. This is what we would expect. or we would think to expect naively. But what's actually happening is remember that it's going to be const x, and const x is going to return. It's going to ignore the rest of the thing. It's just going to be const underscore, which means this entire thing is lopped off. He's like, what's the first value that we're passing into the const function? It's 1. All right, it's 1. It's always, that's it. It is pruned off the rest of the cases. Okay, there is a comment here. I guess that const can take multiple arguments even though it ignores all but the first. Yes, that is correct. Const does take multiple arguments. And another question here, what is the difference between a const function that takes a parameter and ID? I'm guessing the question is related to identity. That's a very good question. I'm not entirely certain, but I'm guessing that ID is a single argument function. Yes, I think the main difference is ID is a single argument function that returns the same value, and const is a double argument function that returns the first value. That's the only difference. I don't know if we could do this. Yeah, this will not work. So the question is can we pass in const with just a list and get the first argument? No, that is not the case. Const requires, the signature of const requires 2 arguments, and it's always going to ignore the second argument. Okay, so the comment about it is can we pass in a single argument to const? And that, as you can clearly see here, const will not allow that. And again, it goes back to the signature. The signature explicitly tells you it requires 2 arguments. You need to, if you don't pass in 2 arguments, you're going to get a partially evaluated function, like in this case right here. And in this case, what we're doing is we're going to return the list, regardless of what's being passed into the second argument. So why is const so important? Well, const becomes important when you're dealing with this undefined bottom value that we were talking about earlier. I mean, we could totally see const being used as passing in, say, undefined, and we'll notice, oh, right. My apologies. I keep forgetting that I have to put this in the dollar sign. So we'll see that this here, if we pass in undefined in various shapes or form, it as long as undefined, it goes back to what I was saying earlier, as long as the collection contains an undefined somewhere else in the list, we are okay. And as you can see, this doesn't, though, prevent const from not, being throwing an exception if you have a undefined as part of the top of the list, okay? Because naturally, that's going to immediately be evaluated, and then it doesn't matter. Whereas fold right has this kind of evaluation. Fold left has a slightly different evaluation, okay? Remember, the way folds work, we have to kind of go through the spine from beginning to end, okay? Fold left does a slightly different approach than fold right. Again, though, if you look at fold L and if you look at fold R, the difference between fold L and fold R is the fact that the fold L expression requires the 2-argument expression to be B to A. It's going to be B comma A first. So that means the initial value argument is going to be essentially the initial value that's going to be passed, first argument that's going to be passed into the reduction function, whereas in fold R, it is the second value that's going to be passed in. What does that mean in terms of evaluation order? Well, let's quickly look at an example. Let's walk through a quick example of addition again. Okay. Remember, and it'd probably be better for me to put this here. Let me just pull this guy down and cut this guy off. And okay. So we have our fold out expression. We're going to just do 3. So whereas, and let me also, before I do this, let me just go ahead and quickly write a potential implementation of this guy. So if we do this, and we pass in the function, the accumulator, and the empty list, we get the accumulator, and then we do, let me just do this here, and here, and paste that, cut it, bring that down, this, bring that, okay. And we have our fold L F accumulator and our actual non-empty list, in which case what we do here is we do fold L, apply F on F of the accumulator and current value X, and then the rest of the list. All right. Again, this is slightly different than what we saw earlier. We did F of X in our earlier part of the discussion. We did a simple F of X, and then we'll apply the fold operator here. In this case, though, you can see that what we did is we applied F first to it, and then we got the result and passed that into fold L. How does that change our evaluation order? Well, what this does is it makes the ordering left associative. Okay, so how does that pan out when you run this? Okay, so this obviously is going to be the same as fold L plus 0, 1, 2, 3, the empty list. Okay, this hasn't changed at all. Okay, and we're now going to apply the operator on the first thing. So what does this mean exactly? So the first call is obviously going to be fold L plus, okay, of 0 plus 1, okay, and 2, 3. Next call is going to be now fold L plus 0 plus 1 plus 2 and 3. And then finally we have fold L plus 0 plus 1 plus 2 and then plus 3 on the empty list. Okay. Now we hit our base case. Okay, and our base case obviously means we're just going to return the accumulator. So here, finally, what we're going to get is 0, 0 plus 1 plus 2 plus 3. Okay. So we actually do an additional evaluation here. Notice we've evaluated 0 plus 1 plus 2 plus 3. We may end up, in the case of actually, because it's a strict evaluation with addition, may actually return the value for 0 plus 1 first, and then do the result of that, which is 1 plus 2 again, and that's going to be 3. So 3 is passed into the recursive column, 3 plus 3 is 6, and then we're emptied, and then we just return 6. So this expression could certainly be evaluated in real time as we are accumulating, all right? Or you can actually get the list itself. So this is how it associates. Notice the difference, though. This is our evaluation of fold L versus our evaluation of fold R. It's 1 plus 2 plus 3 plus 0. Okay. In one case, we are applying the initial value at the very end, okay, after doing a depth first. In the other case, we're doing evaluation at the beginning, which is kind of a breadth first evaluation. Okay. Okay. This is particularly interesting because this can show you now, and I think this is going to be, again, particularly interesting to see if we do this in the REPL. Let's see this one thing, which is fold R. Let's apply XY concat this list. This is the trick that I was mentioning earlier. And then we do x, comma, and then let's do plus in this case, plus, and then y, comma, then we have this. And then let's do 0, and let's do 1 to 5. Oops, sorry. Let's do zero, 1 to 5. And we'll see. Oops, I messed that up. It may have. Hold on one second. Oh, right. This here is going to be, hold on a second, this, cut that guy. Oh, got it. I have to do this. $sign map show to get the individual characters. Not may show, map show 1 to 5. Okay, so this is the fold R evaluation versus if we just simply take this guy, move it, and we get the same thing before, which I think is pretty neat there, that you could actually look at the differences between the two if you apply additive. This is, again, just the additive reduction operation, okay? And this reduction that we see, this fold L, left fold, is what most people associate with reduce. It's a fold L. We start with the initial accumulator value, and then we work our way through the list until we get the final element, which returns a list. Another things that we can use is to see how folds evaluate, because we wrote this kind of thing, is something called a scan. All right, a scan is like a fold, but what it does is it returns the intermediate results. Okay, so you can use both scan R, which is a right scan, versus a scan L, which is a left scan, to go and look at the results of these guys. And if we look at scan R, you'll see that it looks very similar versus scan L, and you see that that's there. And if you actually look at scanr and scanl, they essentially call foldr and foldl accordingly to it. Okay. Each fold will end up returning the same kind of intermediate results, but the ordering, at least with respect to the particular operation, is going to change. So if you look at it as an example, our fold R of plus 0, 1 to 5, which gives us 15. If we use scan R on the same operation, 1 to 5, we'll see that we'll end up getting the intermediate results that ultimately gets called here. So again, this starts from the right and it works its way up. So here, think it's in reverse order here. So it's going to be 0 plus 5, obviously is 5, 5 plus 4 is 9, 9 plus 3 is 12, 12 plus 2 is 14, plus 1 is 15. Okay, and if we do a scan L, if we do a fold L first off, fold L on it, the difference between this and that is going to be just the ordering and how the addition is going to be applied. So if we do fold L here, we also get 15, but if we do a scan L on this, we start with 0, add 1 to 0, add 2 to 1, add 3 to 3, 2, and so forth. So it's going to be 0 plus 1 is 1, plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So this ordering of the scanning should tell you how the associativity is actually working around. There are some effects of related to associativity when we are talking about left fold. Again, and I know I've been kind of like this has been kind of the what's the word, the running theme of this chapter is about how deconstruction works. But we've talked about constant folds all do some sort of spine traversal in the same direction, all right? Well, we've talked about all folds doing some sort of spine traversal. What we didn't talk about is how they're doing it, right? Fold L and fold R are using the same spine traversal code, all right? They are doing it left to right, iterating through every element, okay? But because of the associativity and how it's going to be ultimately evaluated, it changes the intermediate results, okay? Remember, associativity, just to talk about associativity, left associative is A plus B plus C is left associative. That's what we saw earlier. Right associative is A plus B plus C. Okay, this movement of the associativity changes the actual intermediate results that are going to be occurred as a result of the evaluation. And this is all related to how to think about evaluation in Haskell in general. And that is because we're using lambda calculus, substitution would probably the best way to actually do this. When we're using a right fold, especially, we are actually dealing with when we're doing right fold or left fold, we are dealing with how the evaluation is going to occur, right? We saw that already with evaluating, we went through an evaluation of both fold R and fold L. We saw that what we're doing ultimately is we're applying the operation to the use case, okay? So in this case, when we're talking about fold R, we are actually applying the operation in a manner such that we are applying it so that the folding function actually occurs in between our first argument and our second argument. Okay, this evaluation could easily be written if you feel more comfortable to doing for 1 plus 2 plus 3 plus 0. And generally speaking, this is going to be applied that same way, where we have some sort of generic for a given. I'm going to go ahead and write this generically. Let's write this down again at the bottom. So we know that we have this, but generally speaking, given some sort of folding function, f, this here could be applied if we do fold R f on some sort of list, okay, given some identity. Let's take 1, 2, 3. In this case, we're going to be our identity 0. This can be written as R f f f. Remember, when you're using Haskell and you're trying to use an operator has infix, you want to apply it with a single quote. So let's go ahead and apply this here, get this out, and then get this out and do that. So this is what it's going to kind of look like, right? Is you're applying the operation, you're iterating through the list still left to right, you're hitting some sort of base case, you apply the identity, now the expression is fully formed, substitution is done, you can't actually do any more substitution, so now you can do full function application. This falls straight out of the lambda calculus using the substitution property given the initial values of the data. I encourage you to work through this for any sort of kind of examples until you become comfortable with this, but this is a very important thing to know. And this, regardless of function call that you're dealing with, when you're dealing with this, this is kind of the evaluation rules. This is also a direct result of the fact that Haskell is lazy evaluated too as well. It's dictating kind of the order in which things are going to get evaluated based on those rules. Okay, so the parentheses and the ordering of them are determining the order in which it's going to evaluate. Okay, and the rule of thumb, at least for Haskell, is innermost parentheses are going to be evaluated first. So when you're dealing with fold R, that means, again, it goes back to what I said earlier, this depth first evaluation. The last expression, because it's been fully formed, it's going to be the first expression that's going to be evaluated first, since it is at the top of the stack. So it's going to compute its value, pop off. The next thing is going to compute its value, pop off, and so forth until we empty the stack, and we'll have our final result returned to us. This is at least how I've kind of thought about it. It's basically the stack operation. You're pushing the operation onto the stack, and then you're going to continue the recursive call until you hit the base case, and then you have all these expressions in this stack of expressions, and now you're going to do the actual final evaluation. So you're traversing now the evaluation of the final expression inside to out instead of outside to in. Okay, so list traversal is going to be outside to in. You're going to start left to right, but you're building up the expression when you're using right fold. Right, you're building it up. You're not actually evaluating. When you're using something like addition, it becomes very hard to determine to see this, just mainly because addition itself is a commutative operation. Okay, what do I mean by commutative? Well, going back to our good old friend arithmetic, right? I'm sure most of you remember this commutative property, where you have some operation. In this case, I'm going to use plus to be some generic commutative operation. A plus B equals B plus A. So it doesn't matter the order in which you actually put the things, it actually will not affect the final result. But if you pick something else other than addition, the right associativity becomes very, very important. Okay, an example of this is probably the best one is going to be using exponentiation. Okay, everyone knows exponentiation. A to the x is just repeated multiplication. Okay, so a to the x is, let's say a squared equals a times a, and so forth. What we do is let's say that we wanted to do a fold r to actually compute kind of like the exponentiation of different things versus fold L. Okay, let's use this for powers of 2. And this is an example that I've seen in the book that I thought was good to cover. If we do a fold R of this, okay, and we do plus, a caret, and remember caret is the exponential operator. It's going to just take an integral and then take in 2 values and then return a value. All right. If we do a fold R on this with 2, okay, and 1 to 3, what we're going to do is we are going to, 2 is our initial value, okay, but we actually haven't actually computed the values yet. So we actually would start with 1, and then remember we call the exponential operation on the rest of the list. Then we start with 2, we keep going, start with 3, we keep going, and then we go, and then we end our evaluation, in which case we hit the base case and we replace it with our identity. In this case, it's going to be 2. We at least set our identity or our initial value is going to be 2 here. So now we have our full expression. It's 1 to the 2 to the 9th. Okay, so we start with the 9th. So if we give this in, this should not cause any issues. Okay, so this here first is going to give us 2 to the 9th. Okay, which is now, it doesn't, 2 to the 9th is technically 512. And then we get 1 anyway, because 1 to any x power is going to still be 1. But if we change this to fold L instead of fold R, as you saw before, fold L, and we can actually see this with scan R. Let's do the scan R version of this. We got this, 1, 2, 3. We started with 2, 2 becomes 9, and then 9 becomes 512, and then our intermediate substance is 1. If we did fold L though on this, 2, 1, 2, 3, this is actually going to become very different. It's going to be 2 to the 1, and then that result is going to be 2, which is to the squared. It's going to be 4, and then it's going to be 4 cubed, all right? Which is 2 to the 6th, which is 64. When we could see this when we do scan L, right? This is the same thing. The associativity becomes very, very important to change, okay? And this is going to be important when we start talking about writing our own fold expressions, okay? I'm gonna pause for a minute for questions. I'm just going to briefly mention, review this one thing, which is our function signatures for fold L and for fold R. Okay, the way you want to read this is related to the types that are being passed into the function itself, right? The again, fold L, which takes in a 2-argument function, okay, The parameter of type B represents either the start value or the current intermediate result of the current running fold that we're performing. The parameter that's of type A is usually the parameter representing the list that we're actually traversing through. And this occurs regardless of fold L and fold R, right? In the case of fold L, the start value or fold accumulated so far is now the first argument, whereas in the case of fold R, it's the second argument to the function that we pass in the intermediate result. But then the same signatures are all going to still apply. They all require some list of, after this function and initial value is provided, we require some list or some foldable structure to be folded on, and then we'll return the type of the folding expression. And the type is always going to be the type of the initial value. Okay, that they have to match. In the case of conses, let's see one thing here. So let's apply this associativity to the case of conses. Let's look at fold R of the cons operator, starting with the empty list and putting in 1 to 3, versus fold L, which does the cons 1 to 3. Which will give you an infinite type. Cannot construct the infinite type A to list of A. First argument is occurring to that's right. So why did the fold R work, but the fold L didn't work? Well, the reason is what cons actually expects. Okay. Cons expects that the first argument is going to dictate the type that is necessary for the list in order to actually construct a list. Okay, we can go back to looking at what cons actually tells us. Cons actually tells us that it takes in a list and gives you the rest of the list, right? And if it doesn't get anything, it'll return nothing. So, not providing anything here and then doing the cons on this is not going to give you any issue, because it's going to give you an issue because one is a numeric and the other side is some sort of is not a it's not a numeric type. Okay, the cons operator sees that as a type mismatch. So, whereas in the case of a fold R goes back to what we said. We're traversing through the structures until we hit the base case. In which case, in the base case, we can actually apply the empty value, and then the rest of the structure can now be cons. So it's okay to have 1 colon empty, but it's not okay to have empty colon 1. We cannot, and it's related to how lists are constructed again. A list is prepended to, it is not appended to. So in this 1 colon empty list, we are prepending 1 into the empty list. Okay, it's going to go into the front of the list. All right. Whereas here, we're attempting to append our list, which we can't. Okay, that's a very important distinction, which means fold L for certain types of expressions. If you're dealing with lists that are already non-empty, you're okay. It allows you to do this. But fold R is more general because it allows you to do certain things a little bit more, because it waits until the base case gets hit before it actually goes and runs an evaluation. Now, there's one thing that I'm going to introduce, and that is there is one way of actually fixing this one issue, which is let's go ahead and call, because sometimes we may want to append to a list. There's a function in Haskell that allows us to literally take the backwards arguments and flips them, all right? And it is appropriately called flip, okay? If we look at flip signature, all it is, it takes a function of two arguments and flips the arguments. So if we do, say, f equals flip that, now we can actually get something interesting. We could do flip colon, okay, and then start with an empty list, and then 1:3, and you'll see that what it does is it will actually flip it and say now it's one. So in this evaluation, and let's go ahead and we can also do fold L f empty list 1:3. All right, and it's the same thing. But when we go and apply this, how does this get evaluated? Well, fold L, let's write this out. Flip empty list 1:3, okay, which is 1:2:3. What does this do? Well, first off, we know that it's going to go and apply fold L, flip, colon, and then our initial value now is actually 0, flip, colon. Actually, it's probably better to write this like this: flip, colon, empty list 1, and then 2:3. And what that does is it's actually creating the following. Okay, it creates fold L, flip, colon. Instead of 0, the empty list being like this, colon 1, what's going to actually be applied is now 1, colon, 2, colon to the empty list, and then we applied this. So effectively, we've now gotten the original thing here, all right? So the next thing is and I think it would be easier for me to, and I just showed the simple example, but let me go and fully evaluate this guy. So to simplify things, I'm going to say let f equal flip, colon. So this way we shorten the expression a little bit quickly. F, oops. Okay. Okay. let's just quickly go through this. Fold L, F, F, 1, 2. Three, fold L, F, F of F. And it's probably be easier for me to do it this way. Probably better for me to write it this way to make things even more obvious. F, F, okay. And now we have our final expression coming in. F of 1, F of 2, F of 3, empty, and now we finally hit our base case. And our base case is going to be empty list and the accumulator anyway, so we finally returned this guy. All right. So we now have our actual expression here. Actually, it's probably easier for me to do that. So now we can now apply the flips. So this is going to become 1 colon. Okay. Now this is going to be the second argument to the second flip. Okay. So it's now 2 colon, because we now flip those signs. And this is going to be the last argument of 3 colon. Okay. You see that there? So this is essentially what we've done. The flip automatically flips the arguments every time, and it will always flip the 2 arguments and give us a valid expression in this case. So we'll end up reversing it. So if we wanted something similar to what we did earlier with fold L and fold R, you could certainly do something like this, where if you wanted to be always the concat to be regardless of fold L and fold R to return the same results, this is essentially going to be nothing more than a reverse on fold L, F, and you'll see that you'll get the same result as fold R. So, what have we learned? We learned that flip gives us this interesting thing by flipping things around and gives us essentially something that, but still it will return us because of the left associating nature, it will give us a different result from fold R. We have a couple of other things related to const, and I think const is important to understand. And we talked about const again earlier, which it takes the first value and prunes it. Since it doesn't exactly evaluate the second argument, it means that if you flip const, it's going to attempt to give us differing results. So here's an example of this, okay? Fold R, we talked about const earlier when we did const 0, 1, 5. We knew that the first evaluation of the non-empty list is going to give us 1, and then the rest of the evaluation is going to give us wrong. But if we go in and actually say flip const instead, and we do 0, the reason why we are getting 0 instead of that is at the end of the evaluation, we are actually starting with the innermost case, which is 0, and then working our way up. The difference here with const is if we do left associativity, if we start with const on 0 and 1 to 5, we'll see that we'll actually get 0 first. But if we do fold L flip const 1, 0, 1 to 5, we'll end up getting 5. And again, this is the effect of the associativity of the operation. So this is important to know. The associativity of the operation does not affect traversal, but it does affect evaluation. It does not affect traversal, but affects evaluation. This is a very important thing to just keep in mind. And because it affects evaluation, it could lead to different results, whether you use a left fold or a right fold. And you are using a non-commutative operator, because again, commutative operators, that's their specialty. They, regardless of the association, they will return the same results. So if the operation is commutative, left fold and right fold will give you the same results at the end. But if it's non-commutative, then you are dealing with differing results depending upon the associativity of the operation. The biggest difference between fold L and fold R is the left fold gives us successive steps of the fold of its first argument, whereas the right fold doesn't. Okay, the right fold waits until the recursion is unconditionally invalidated. But the next recursion isn't intermediated by in fold L as it is in fold R. So in both cases, the traversal is going to be the recursion of the spine is going to complete itself. All right. And because it doesn't force evaluation, because it's not eagerly evaluated, nothing will potentially change. And we've seen that with examples like, const again. We've seen const with undefined. We've seen flip const with, if we do flip const with undefined, we'll get the same error that we did before. And we've seen examples of using undefined that kind of illustrated this earlier in the course of our discussion. Because of this unconditional evaluation, fold L has a specific limitation in it, because it would end up throwing potentially an error because we hit the bottom of the spine, and we must evaluate the spine in the case of fold L, and not necessarily as in the case of fold R too. But it's also interestingly inappropriate because of the fact that it's also inappropriate because of example. Let's see this. So let me show you an example here as to where it will be potentially problematic. We've looked at, yes, let's start with this example from the book. We have this, okay? We fold R on const 0 x's, we have nothing, right? If we go and fold R on flip const, we have this problem. Because again, we have this unconditional traversal. Sorry, no. That x's. There we go. And we have that. And we have the same problem here. Fold L const 0 x's. We have this problem. But if we end up trying to do flip const on this 0x's, we also have this problem. So it doesn't matter if we do for fold R, it matters whether or not we flip the const or we don't flip the const. But with fold L, it doesn't matter if we flip the const or don't flip the const because we have to traverse through the entire array. We started out with the successive steps to actually go through and actually evaluate the entire expression, which includes the undefined value that's in the list. Now, since it is the reason why it's throwing this is because since we have to go and traverse through every value, and undefined or bottom is in the spine, we have to go and evaluate it. Now, what's interesting is if we end up using this case, and again, this is just another example, undefined, okay? X is in the exception of the undefined. This is slightly different than what we had earlier. X is 1, 2, undefined. Let's do this. Actually, I take that back because it's the same defined regardless. But in this case, we're okay because if we do a fold L, let's see, 5, 0, x's, we still end up getting 5. In this case here, we're okay because of the fact that we are ignoring both arguments. The Haskell compiler, the Haskell REPL, recognizes this, and it prunes the undefined out. And even though we do expect it during the course of evaluation, it is appropriately ignored. So what this is teaching us is the fact that, in general, when you're dealing with potentially infinite lists, fold L might be inappropriate to actually use because of this forced evaluation of the entire structure to construct the actual final expression needed for evaluation. But if the combination also fold L, left fold, is probably also inappropriate for potentially long lists, like lists that have millions upon thousands, maybe even millions upon elements, because traversing through everything requires kind of significant results, which will affect the actual performance negatively. As you are going through, you are actually accumulating from the start all the way up, whereas with the right fold, you are actually only accumulating as much as you need. You can actually lop off part of the list if you need to. And that will affect performance when you're dealing with the left fold. Because of this, and this is related to the non-strict nature of and lazy nature of Haskell, if you really need to use a left fold, there is a eager version or strict evaluation version of fold called left fold called fold L prime. I think that might not be available. Or fold 1. It might be now called fold 1. Let me see. Import data.list. I thought it was available. Yeah. So fold L prime is part of data.list. It's not part of the prelude, unfortunately. If we do info on fold L prime, you can see that it's actually defined it's defined in data.foldable, which I think is imported when you do import data.list. And this actually strictly evaluates your list or your foldable structure and allows you to actually go and eagerly evaluate all the values associatively successfully. And this also means that the performance effect is less on when you're traversing, especially long lists. Okay, so it's going to be more performant than fold L on long lists. So we went a little over, and I didn't get a chance to complete this, but I'm going to end it here. Next week we'll finish off our discussion on folds by talking about how to write our own fold functions, foldables, and go into a little bit detail on scans. That will be, again, this Thursday, September 30th, I think it is. And until then, I wish you all a good Sunday. And I'll talk to you guys later. Bye.